Welcome to week 10, module 46 of Database Management Systems course in the IIT Madras online B.Sc program. The last week was spent on discussing various aspects of data, physical data organization, design considerations, accesses, indexing, hashing, and how to do that, what you should be doing in the real application. This week, we will introduce and discuss about transactions, right. So, you had design, you had the runtime data organization, the physical design, and now you have the operations to learn about, that is the transaction, and particularly learn about issues in concurrent transactions. So, first to define the concept of introduce the concept of a transaction. Transaction is a unit of program execution. So, it has a couple of one or more sequence of instructions. And what do? They can access, that is read, they can update, that is write, and in between they can do several other typical computations of programming languages. So, here is a transaction, sample transaction, which we will keep on using as a running example for explaining several ideas. Transferring $50 from account A to account B. So, naturally what you will have to do, read A, first know what is the current balance in A, subtract 50. We are making a simplifying assumption here that the account has more than 50 or more dollar available. So, that this can be done. In reality, there will be a condition check also to see that there is enough balance, otherwise you will have exceptions thrown on that. So, you deduct the value. So, A has now $50 less. So, you write that value back. So, A's account has been debited by $50. Then you read B, and we will have to credit that amount to B. So, you take B, add 50, and that is the new value of B, you write it back. Right. So, with this what will happen? Account A has been debited by $50, account B has been credited by $50, and the transaction has taken place. So, this is the basic idea of the transaction. Now, we will have to remember that failures of various kinds, there could be a hardware failure, software failure, system crash, and so on. So, the transaction, and these things can happen at any point of time. So, what happens to the transaction when such failures happen? And second, how to handle the concurrent execution of multiple transactions, that how to allow two or more transactions work with the same data at the same time, at the concurrent time, in a certain with certain restrictions and collaborations to have better system performance. So, there are certain properties of a transaction that those are acronymed as ACID, Atomicity, Consistency, Isolation, and Durability. ACID is a very basic concept in transactions and very important, and like any interviewer usually has a propensity to ask questions around ACID, right, ACID. So, be on top of it. So, the first thing is atomicity, in that when I do this transaction, suppose I can have failure at any time. So, suppose this write has been done, up to this point it has happened. Now, the system fails at this point or at this point. If it does, then you have an inconsistency in the data, because A has been debited by $50 and B has not been credited by $50 yet. Right. So, if it happens at any of these points, if the failure happens at any of these points, then $50 simply vanishes from the system. Right. So, you have to ensure that updates of a partially executed transactions are not finally reflected in the database. So, we say this is atomicity, which means that either all of the changes go on correctly, completed and reflected in the database, or nothing actually happens. So, that the state of the database here and the state of the database here would remain same if you did not do anything. Right. So, atomicity is looking at as if this is an atomic operation. So, if you are if you recall your operating system, you will remember that we had atomic operations there to make sure that critical data, critical sections are either executed or not executed at all. Partial execution is not allowed. Consistency talks about actually having the database in a consistent state. So, what is the consistency in this problem? $50 is being transferred from account A to account B. A is debited, B is credited. So, before the transaction, the value of A plus B that you had must be the same after the transaction as well. The value of A plus B here and the value of A plus B here must be same. So, this is an invariant. So, that cannot change. If it changes, then the database is not consistent. Right? So, there could be the consistency requirements could come from specified integrity constraints, primary key, foreign keys, they try to guarantee consistency, or there could be implicit, like the sum of balance of all accounts minus the sum of loan accounts must equal cash in hand. Whatever you have in accounts, whatever loans you have taken, and you take out the loan liability. So, this is sum of balances is your asset, loan is your liability. If you subtract, what you should get is a cash that you have in hand. If this gets violated, you have a consistency problem. Right? So, a transaction when it starts executing, it is a consistent database. During execution, there may be some inconsistencies created, we will see, but at the end, it has to be again back to a consistent state. Right? So, that is the second property. The third is isolation. Isolation talks about if more than one transactions work on the same data, it might guarantee that no inconsistent database update is made available. So, what you can look at here is there is a transaction T1, which is what we have been dealing with. There is another transaction T2, what it does, it reads A, reads B and prints A plus B. Now, what if I do them concurrently, so that first these three are executed in transaction T1. So, what has happened? A has got debited by 50 and then this gets executed. What will happen? It will read an A now, which is less by 50, B has not changed. So, when it prints A plus B, it will print a value of A plus B which is 50 less than what it was when T1 started. And then T1 will complete, it will again become consistent, but at this point it will give you a value which is an inconsistent value. Right? Now, obviously, if you run T1 and T2 serially, that is if you run T1 and then you run T2, or if you run T2 then you run T1, then it will always reflect a correct consistent state. So, this is called isolation, that is two transactions working concurrently should not impact each other in a way that database becomes inconsistent. Right? So, if you run things serially, obviously it will be guaranteed, but in general that will not give you the desired throughput. Finally, durability is after the transaction has completed, then the effect of that transaction must be persistent in the database, even if further failures happen. Right? After the transaction is successfully completed, the database has come to a consistent state, and that state must stay on for any irrespective of any other failures. That is called durability. So, this is your asset. Here I have in one slide summarized the basic atomicity, consistency, isolation and durability properties. This is more for your self study, but is exactly what we have discussed. And I find this quick reckoner a very useful thing. Is in one slide, very in a crisp way, atomicity is all or nothing transactions. Either you do everything in a transaction or have no effect of the transaction. Consistency guarantees committed transaction state. Isolation says that transactions are independent, and durability says that committed data is never lost. Right? Get them not only by heart, but by your realization. Now, transactions are like processes, right? You have known processes, threads. So, in operating system you have seen that there are states in which a process is. Similarly, a transaction could be in several different states which are described here. Let me go to the state transition diagram and explain this. So, this is a basic state transition diagram. Initially, the transaction is in active state, that is when it has begun. So, what are the possibilities? One possibility is it will do some read write operations, and when it has done some read write operations, it comes to a partially committed state. Right? Now, whether it is partially committed because it still has not completed. So, it does not have a persistency, does not have a consistent database yet. So, it is just some commits have happened, others have not, and so on. So, if you have a failure while you are in active state or when you are in partially committed state, you go to a new failed state. Right. What you will have to do in the failed state? Certain things which you have already done, you have to undo them, that is rollback. The transaction rollback, this much has been done, this has to be undone, right. Those read A assigned A minus 50, write A, then things have failed. So, you have to roll back that write to get to the original value. So, as you roll back, you come to a state which is called the aborted state, because your transaction could not go through. Now, there are two possibilities. One is the system can decide that this was a software error, and particularly for software error, logical error, and correct for that, and it could restart. If it restarts, it is back to the active state. The other possibility is the failure actually is some hardware or system failure, in which case you cannot actually proceed. So, you have to kill the transaction and you come to the terminated state. On the success side, from the partially committed state, if you did not have a failure, then you write back to the permanent store and the transaction goes to a committed state and you are done, you come to a terminated state. So, this is the life cycle of the transaction, the different states and their transition. This is just logically obvious, but you have to learn this diagram, the transition diagram and the process, steps in that by realizing them. So, make use of the earlier slide for descriptions. Now, we will talk about concurrent execution, which is the most important thing, that if we had done all transactions one after the other, then the throughput will be very less, because we need to increase the processor and disk utilization. For example, while one transaction is using the CPU, the other transaction can do some disk read write. These are independent, so they can be concurrently done. Also, you can reduce the average response time, because a short transaction which has fired later on, while a long transactions are going on, could be done ahead of the long transaction, so that effectively you have a better throughput. Right? So, these are the reasons you want to have concurrent execution, and for that you need a schedule. The schedule is basically the order in which the instructions are done. Schedule is a sequence of instructions, and those instructions could come from different transactions. So, there are two basic properties of a schedule, that it must consist of all instructions of all transactions involved, like you cannot miss out an instruction. Second, it must preserve the order, which means that in a particular transaction, the order in which the instructions are given, you cannot change that in the schedule. You can only do, but you cannot change the order of instructions within one transaction. It must remain the same. Transaction that successfully completes its execution will have the commit as a last statement or commit by default, and which fail will have abort as a last statement. Right. So, there is two transactions being done. Transaction T1 transfers $50 as we have seen, and transaction T2 transfer 10% of the balance from A to B. Right. And you can see this is a color code. This is the value of A, this is the value of B, this is the value of A plus B, which has to be an invariant. And what happens when you do the transactions in different times, and we use the color codes to show the times when it is the database is consistent, when it is temporarily inconsistent in transit, and when it is inconsistent with commit. Right. So, here you are first doing T1 and then doing T2. So, you have start with a consistent state, deduct $50 from A and write back. So, as T1 writes A, then you are into a inconsistent state, because you see that the total has become 250. So, $50 have vanished, but this is in transit, this is just temporary. Then you have the write B of T1 happening here when the added $50 are written back to B's account, and you are back to the consistent state. T1 has finished and committed. Similar things happen here. You read A and reduce it by 10%, 45, temporary inconsistency in transit, write back of B, it becomes consistent. So, the sequential or the serial schedule will always be consistent, right. But you could, what if you did T2 first and then T1? If you did T2 first, then you will first deduct transfer 10% from A's account to B's account, and then transfer $50 from A's account to B's account. So, earlier A was having $45 and B was having $255, but now A has $40 and B has $260, because it is a different serial schedule. This is not an error. In a database concurrent system, this is perfect, because the database has never got inconsistent. It does not know which transaction has to be done first. Every transaction is complete and valid in itself. Right. If you have to enforce that no, this is not possible, then you have to design the transaction in this way, but both of them are consistent at commit. So, they are valid schedules. Let us do a third schedule, which is not actually serial. So, what we do in the third schedule is transaction T1 first reads and deducts A, you get here. Then transaction T2 reads that A and writes it back, you are here. Then transaction T1 reads B and updates B. Now, what has happened? Transaction 1 has finished, so it is committed. So, you have a commit, but still $5 are not there that you took away in this temp. They have not come into the. So, you reach a state which is inconsistent at commit. It is different from these two, because till then no commit had happened. It was inconsistent in transit, but this one is inconsistent at commit, right. So, this is 295 is inconsistent at commit. Fortunately, as you complete transaction B, which reads and adds back this value, this $5 from the temp back to the B's account, makes it consistent. It gives you the same result as schedule 1, which is shown side by side, right. So, it is possible that during when you have a schedule running concurrent transactions, then it is possible that temporarily transaction the database could be in inconsistent state, even it could be in inconsistent state after commit, as long as you do not have an inconsistent state at the end of both transactions, you are okay with that. Because in all of these schedules 1, 2 and 3, the sum A plus B is preserved to be 300. So, this kind of a schedule 3 is called equivalent to schedule 1, because it will have the same effect in the database. So, we have seen schedules 1, 2 and 3 which are serializable, in that they are equivalent to these concurrent schedules are equivalent to some serial schedule. Now, we will see an example in schedule 4, where the concurrent schedule is not serializable, that is, it is not cannot be equivalent to any other serial schedule. That is, very precisely it will not preserve the sum A plus B, this invariance will not be preserved. So, you can see that we have the same set of instructions in T 1 and T 2 as before, but they are arranged intermixed in a different way. So, first we do read A and perform A, decrease A by 50, right. So, in the local area of T 1, we have A as 50 now, right, when we are here, right. We have read A, which was 100, and in the local it is 50 for the transaction T 1. Now, the next two instruction to execute is read A by T 2. So, transaction T 2 also will read A as 100, right. It will read A as 100, because it has not been changed, not been written by transaction T 1. So, it will still read 100. Then temp is so temp in the local of T 2 is 100 into 0.1. So, temp is 10. So, local in A now, when you subtract temp from A, becomes 90. So, you will write that A. So, transaction T 2 writes that A. So, this 90 gets written, and after this write has been done, you are in a transient inconsistent state, because they do not add up to 300 anymore as they should have. Okay. And remember that the local copy of A in T 1 remains to be 50. Then you read B. So, you read 200, and this is what we have in the local copy of T 2. The next instruction is writing A by transaction T 1. So, it writes A. What does it write? It writes whatever is the value of its local copy, which is 50. So, it writes 50. So, after T 1 has written, the database remains to be in an transient inconsistent state. Then it reads B. What is B? B is 200. So, it reads B. B is 200 in the local copy of transaction T 1, increments B. So, it becomes 250 in the local copy, it writes B. So, it writes B now, this is where it is written 250, and it does a commit. As it does the commit, A is 50 written earlier here, and B is 250 written here. So, right now the transaction is in a consistent state after this commit. Now, this instruction is executed. So, B gets B plus temp. So, B becomes 210, and you write B, and this is where the problem happens, because the old value of A that was written was not the modified value of A that you had computed here, because that was overwritten, and based on that B is getting changed, and so the earlier value of 250 gets changed. So, it is now written as 210, which is the value of the local copy of B in the transaction T2. Consequently, and then when the transaction commits, consequently, we have a inconsistent, final inconsistent committed state. So, this shows that schedule 4 does not preserve the sum. The sum has now become 260, 40 rupees has simply disappeared, and therefore, there is no serial schedule equivalent to this schedule 4, and it is not serializable. So, that is the point that we make, that all concurrent schedules are not serializable. Okay. So, this brings us to the end of this module. We have taken a look at a transaction as a task execution in the database. We have talked about the basic concept, the concurrency, the states of a transaction, the concurrency requirements, and the concept of schedule and how schedules, concurrent schedules may or may not be equivalent to a serial schedule. Thank you very much for your attention, and we will meet and continue on this in the next module.